All right, so chapter 11 is about the modern atomic theory. You remember me talking about that? I've done that 3 times now. And even though it's modern, it was mainly in the early 1900s that this came about. And all these smart people like Einstein and Schrodinger and Heisenberg and all these names you may have heard of when they think about smart people. Anyway, they came up with this idea, and they knew that light had something to do with this. And so, like many, many types of energy, light travels in what they call a wave. And one day I got a slinky out, and we looked at a wave, and we found out that the top of a wave is called a crest, the bottom is a trough. What's the distance between the top and the top, or the bottom and the bottom? Same thing. What's that called? Wave length. Pretty easy, right? Now, we found out that even though sound waves and ocean waves have to travel through a material, light can pass through nothingness. Light can come from the sun, and there are no atoms between the sun and us, except when it gets to Earth. And so when sunlight, any kind of light travels, it doesn't have to travel through anything. That's pretty amazing. It also travels at an incredible speed called the speed of light. Now, even though you don't think of these as being light, every one of these up here, this is called the electromagnetic radiation. When I was younger, I didn't understand what that was, but I figured one thing out. Whenever I heard the word electromagnetic radiation, if I just substitute the word light, everything started making sense. So ready? Electromagnetic radiation comes in many wavelengths. Oh, light comes in many wavelengths. Oh, that's what I said. Some of the wavelengths are really long, 10,000 meters long. Man, that's a big wavelength. And some are incredibly small, like 10 to the 1,000,000th of a meter. So what do we know about these types of light? Okay, we know that they all travel the speed of light. In physics and chemistry, a little c is called the speed of light. Remember, have you ever heard of E equals mc squared? Einstein stuff? The c is the speed of light. Got it? So the speed of light is equal to the wavelength of the light times the frequency. And if you take a look at this, here's what I want you to remember. If you had a really, really long wavelength, how often would a wave come by per second? Not very often, because it's so long. What if you had a really tiny wavelength? Then the frequency of the wave would be high, wouldn't it? So these have long wavelengths, but low frequencies. What's this one? How about gamma rays? Small wavelengths, but what? How often does a wave come by? Really frequent, high frequency, right? Now, why do I tell you that? Because the amount of energy in that wave has to do with its frequency. You have low frequency, you got low energy. You got high frequency, high energy. An hour, being exposed to an hour of that kind of light, you'd probably be all right. You're being exposed to an hour of gamma rays, you're not going to be all right. You're not going to be all right. It's going to hurt you. You're going to die. So look at this little tiny slice of light that we can see. Our eyes can only perceive the rainbow colors, right? We can only perceive between what they call 400 and 700 nanometers. That's pretty small wavelength. But our eyes can, everything I see is between 400 and 700 nanometers. And God said, that's enough. That's all I'm going to let you see. Now, tell me about this one. Which one of these would have the highest energy? Red light or violet? You're right. Because it has a small wavelength, it has the highest frequency, highest energy. Get that? If you understand that, I'll go to the next thing. There's a controversy, it's always been a controversy. Is light like a bunch of BBs? When you turn on a flashlight, are little particles coming out of there? Or is it a wave? In the ocean, the water doesn't move. It just goes up and down. It's the energy moving. So the controversy is light a wave or is it a particle? What's the modern answer? Both. It's both. You guys are remembering a lot. This is really good. You're making me feel good. So it's a dual nature, right? Now, what would they call the little particles that they think light travels in? They're little bundles of energy. What do you got? Photons. Now, so a photon, the reason they drew this drawing here Why did they make the blue photons bigger than the red? Why did the author do that? What do you think? It has more energy. A blue photon would have more energy than a red photon, right? Okay, now if you understand that, I can get into the bulk of the chapter. Okay, so this is a diagram, and it's like a graph. And I want you to pretend that you're an electron. And you're an electron in where you normally are. So let's pretend you're in an atom, and I'm in where I normally am. That's called the ground state. Got that? Everybody got that? I told the other class, how is an electron where it's normally found, how is that like hamburger? How is that like hamburger? Anybody know? They're both in their ground state, right? Okay. You know, hamburgers like you grind up. Okay. You don't like that one? That's not bad. Anyway, so if you had an electron in its ground state, and then guess what they figured out you could do? You can excite an electron. You can excite it. And at one time they said, hey, just like a piece of metal, I give it a little energy, it gets a little bit hotter, a little bit hotter, a little bit hotter, a little bit hotter. But you know what? They were wrong. The best scientists in the world were wrong. They gave it a little bit, they gave electrons a little bit of energy, and they didn't anything. They did nothing. They gave them a little bit more, nothing. But they found out if you gave them the full chunk, this full amount of energy, that's called a quantum of energy. If you give them a full quantum of energy, whoo, they'll get excited and jump to another level. And that's why it's called the quantum model of the atom, because the electrons, they can't just get a little excited, a little bit more, a little bit more. But if you give them enough, they'll go, boom, and they'll jump to the next level. Or they might jump again. They might jump back down, and like this. And they don't slide up and down like on a slide. They jump like on a stair step. And that's why it's called the quantum model. So now, and this will be the last of the review part right here. When you were looking the other day through those spectroscopes, remember that? Remember seeing the bright lines? Were you here? Do you remember looking through the thing? Okay. Here's what happened. We had some neon in one of those, and neon has electrons in the normal ground state, and it looked like nothing. Neon looked like nothing. Then I ran a bunch of electricity through it, and the electrons said, woo, I'm going to get excited. And they made all kinds of jumps. All kinds of jumps like that. So here's what you need to know. Here's one of the electrons, and when it absorbs energy, you won't see anything. But when it jumps back down, to ground state, it has to release the energy. Now, when it releases energy, it'll come in the form of a wave. And many times I'll see in the form of a color. These lines came from electrons not absorbing energy, but releasing energy. Is this too far above your head? Okay, so anyway, my question would be like this. Which one of these jumps that came down would relate to which color? So let's take a look. See the size of these arrows? Which one of these, help me out, Kyle. Which one of these arrows represents the biggest drop, the biggest release of energy? Is it arrow number 1, 2, 3, or 4? Which one's the biggest drop? It means it released the most amount of energy. Okay, that's pretty big, but look at the size of this one compared to that one. And this one's a little bit bigger. So 4 represents the biggest drop of energy. Get that? Now, the highest energy would be which one of these lights? Which one of these lights represents the highest energy? Which one? This one right here, the violet. See that? So this violet light must have been caused by electrons jumping all the way down to here. Which one represents the smallest jump in energy? Let me ask, I haven't asked you, Isabella. 1, 2, 3, or 4? Yes. So which one of those colors would be the smallest energy? Yes. Are you with me this? This is modern atomic theory. It took some top-level people to figure this out. And then they represented it in a book in a way that we can understand it. I don't know all the mathematics they used. I don't. But here this book's trying to represent it the way that I can understand it. All right, so let's get some more scientists, okay? We know that Rutherford, from the first semester, he figured out the atoms have a nucleus, all right? Nobody else knew that the atoms had a nucleus. But one of his students was named Niels Bohr. This guy here, his name was Bohr, B-O-H-R. And I believe that even in the 9th grade, didn't you draw all these for Miss Founds? Mrs. Founds? You might not have been here. Okay. But the Bohr model is where you put the nucleus, you show how many protons, how many neutrons, and then didn't she have these little circles, like the first energy level, the second energy level, remember that? And you had to remember that how many electrons could fit in the first energy level. Do you remember this from 9th grade? You remember anything, Daniel? Did you have Miss Founds? Yeah. Do you remember doing this? Do you remember how many electrons went in the first energy level at the most? Wasn't it 2? If you don't remember, I'll tell you anyway. It was 2. Do you remember, anybody know the number in the second energy level? It's a bigger energy level. Uh-oh. Somebody said it. How many? That was close. 8. It was 8. Got that? So what I'm going to do is I'm going to try to tell you what they mean. In the 9th grade, she used the Bohr model because the electrons look like they're sitting still. And you say, I see them. There are 2 right there. They actually travel at near the speed of light. Nobody can ever, they don't sit still. But in the model she used, she wants them to sit still so you can look at them. All right, so Bohr, he comes to this model, and he says that the electrons, he said the electrons can be in a ground state, or if you give them a quantum of energy, they might jump to the next level or the next level. And so I like the idea, he came up with the idea of a quantum jump. Now, if you read the book, it'll tell you that the rest of his model was not correct. Bohr did think that the electrons went like planets. They thought the electrons went around the nucleus like planets. When I was taught in elementary school, even in middle school, they still kind of teach that, don't they? Don't they teach the electrons are kind of going like this? Because kids understand planets, so they think that's it. We have no evidence at all that they go in circles. So you're not going to like the next thing I tell you. They're not traveling in circles. Now here's what you're not going to like. What are they doing then, Mr. Smarty Pants? What are they doing? We don't know. One guy named Heisenberg, he says, if you try to figure out where an electron is, can you imagine being in a dark room, a really dark room, okay? And all of a sudden, a mosquito hits you in the face, right here. And you go like this. And later, you go out of the dark room and you said, yeah, I found him. I know exactly where I was when that mosquito hit me in the face. Well, here's what Heisenberg would say. As soon as you stopped that mosquito, as soon as you stopped him, you knew where he was at. But did you know where he came from? Did you know where he would have gone if he hadn't hit your face? No. And that's the same thing with electrons. You can't know where an electron is right now and also know where it came from, where it's going. So we don't know what they're doing. And you're not gonna, I know you don't like that because you like to know. That's okay. It's called Heisenberg's uncertainty principle. We'll maybe always be uncertain about it. Uncertain. These 2 people here, their name was de Broglie and Schrodinger. They were top-level physics people. And they used mathematics, and they said, you know what? We've been treating electrons like little particles. What if we try to have waves? And then all of a sudden things made sense. And that's called the wave mechanical model. So I do tell you, on the test that we have, or the quiz, if it's a quiz, I have a lot of vocabulary words. So you want to make, maybe the first 15 or 16 questions are matching vocabulary words, okay? So they came up with the wave mechanical model. Wave mechanical, yeah. Now, let me show you what this other guy did. Now, watch this. See that fuzzy little picture there? They used mathematics and said, well, tell me then, how will I know where the electron is? And they said, well, here's something we did discover. We discovered that there's one place the electrons are, and it's in this little ball-like area. and they're going to call that thing an orbital. I hate that name because it sounds like it's an orbit, but it's not. It's just called an orbital. Now, anyway, this is called an s orbital. It's an s orbital, and I don't need to tell you why they called it s, but if you want to give me the wrong answer, it looks like a sphere. That's not why they called it s, but that's close enough to remember it, okay? An s orbital looks like a sphere. Now, here's what they found out. The electrons are in that somewhere doing something 90% of the time. Matter of fact, 10% of the time, it might be over here. It might be here. We don't know. But 90% of the time, it's going to be found there somewhere. Now, the reason you don't like this lesson is because there's a lot of, what? You don't know for sure? Okay. Well, that's what we're dealing with, right? But they've discovered a great deal of things from this uncertainty. So here's when I get to the bulk of the lesson. Here's what I want you to do. I want you to see if you can follow me here. All those lines, those colored lines, and mathematics said that the atom has what they call energy levels. So for Miss Founds, it was the first circle, the second circle, the third circle. Now what you do is get used to looking at the periodic table. Okay? Now, these are called periods. Period number 1 has 2 elements in it. Everybody got that? Period number 2 has how many elements in it? That's a quick answer. How many? 8. Period number 3 has 8. And then we start getting 18, 18, 18, 18, okay? So what I want you to know is how many periods are in the periodic table? That's the first question I want you to know. How many different energy levels? Here's energy level 1. Here's level 2. Here's level 3. See how I get further away from the nucleus? Level 4, level 5, level 6. How many do you have? 7. All that mathematics said, you know what? We have elements here that have electrons in the 7th energy level. That's all we know of right now. We know there's 1, 2, 3, there's 7 energy levels. That's basic. Number 1, basic. How many energy levels are there? 7. Now the next thing they found out is that within the energy level, they had these funny drawings, these fuzzy drawing things, right? And it says, in the first energy level, there's an orbital that looks like a ball, and that's called an s orbital. Now, if you'll stay with me, I'll show you this pattern. There's a pattern here, get it? All right, so here we go. In the first energy level, there's an s orbital. Just pretend like that's like an apartment. And any orbital that I show you, you can put 2 electrons in it, 2. Still with me? Okay. So what if you were hydrogen? How many electrons would every atom of hydrogen have? You say, am I supposed to know that? Yes. It has 1 proton, and it's a neutral atom. 1 proton, it must have 1 electron. See that? How many electrons does cesium have? 55. Okay, I got you. So if you have 1 electron, where is it? Where's your electron? And this is the fancy word I talked about before. We're going to do a thing called electron configuration. Configuration means tell me how you're arranged. So here's how you do it. I need you to get a piece of paper out, okay? Now, if you already have a piece of paper out, I'm gonna ask you to turn this in, but get a regular piece of paper out. I'm going to help you. We're going to do the first 20 elements. So just, I know you're taking notes, but all I'm going to do is don't tear it out. You don't have to tear it out. When you get done, we'll tear it out. Now, put down to the top, put electron configuration. Electron configuration. And then make a column called element number and say 1, 2, 3, 4, 5. Go all the way down to 20, okay? So at the top, it says electron configuration. And on the side, it's element number 1, 2, 3, 4, 5. And we'll put the symbols for those elements too. All right, so the first thing, it's going to look like this for you. It's going to say electron configuration, element number 1 is hydrogen, okay? Element number 1 is hydrogen. Element number 2 is helium, and it look like that. So just take your time. We'll do them one at a time. And then we're going to do this thing called electron configuration. All right, so how many electrons does hydrogen have? How many does it have? Everybody. See, we're not going to get anywhere if we just answered a question 5 minutes ago and you forgot it already. How many electrons does hydrogen have? Since it has one proton, it's a neutral atom, it has one electron, doesn't it? How many electrons does sodium have? 11. Is that easy? Let's not make this hard. That's not the hard part. So how many electrons does hydrogen have? Everybody. 1. Where is it located? Well, you got to go into the lowest energy level first. That's level 1, isn't it? It's got to be in level number 1. So in energy level 1, and where in energy level 1, I have a house for you, an apartment. What's it look like? It looks like an S apartment. And how many electrons are you going to put there? 1. What's the electron configuration for hydrogen's electrons? 1s1. Now let me read it again. What does this mean? This is energy level 1. So it's in the first energy level. Imagine can you imagine it's a parking deck? And I have level 1, level 2, level 3. It's a weird parking deck because level 1, it only has 2 places for 2 cars. And if you get there first, I'm going to put you in level 1 in the S compartment, and I'm going to put you there facing that way. Now, what about helium? How many electrons does it have? 2. Okay. I'm going to put you in the first energy level, and guess what? I'm going to put you in the same place, and I'm going to put both cars there. You got 2 electrons? I'm going to put both of them there. What is the electron configuration for? Oh, by the way, I'll go ahead and label these. This is an energy level. This is called an orbital. And we have S. Later on, you'll hear about S, P, D, and F orbitals, okay? For right now, we'll probably do S, P, and D. We probably won't go to F. So in the first energy level, in an orbital that looks like a ball, I'm going to put 1 electron. And this right here would be number of electrons. Okay, so let's do helium. 1s2. In the first energy level, in the s orbital, I put 2 electrons. I got to know if we need to stop here, okay? Are you okay with this? Now, here's what's interesting. If you look at your book, the first energy level is the smallest energy level. It only has room for 1 orbital. And that means you only have room for 2 electrons. And here's the magic. If you'll stay with me, I'll show you the beauty of the periodic table. You don't know the beauty of the periodic table. Right now, you know, do molar masses and stuff like that. Let me show you the beauty. How many elements are in period number 1? 2. Why? Why are there only 2 in period number 1? Can you help me out? Make me feel good today? Why are there only 2 elements in period number 1? I know we're just starting, so I'll give you a little break here. How many orbitals are there in level 1? Only 1 orbital. How many electrons can you put in an orbital? 2. After you put 2, you can't put any more in there. That's it. If I had a parking deck and level 1 only had 1 space, and if you parked your car this way and this way, you could put 2 cars in it. You put 2 cars in an orbital, right? I only have 1 orbital in level 1. That's it. What if 3 cars come? What if 3 cars come? What am I going to do with the 3rd electron? I can't put it in level 1. There's no place. So here's the beauty. Watch now. So what happens to an element that has 3 electrons? What do you think? What do you think is going to happen to lithium? If you'll stay with me, by the time we get to the first 10 of these, you're going to be experts at it, okay? I have 3 electrons. Where do you think you're going to put them? Just relax. Let it come. Watch now. What would you do with the first 2? What would you do with the first 2 of the 3 electrons? What would you do with them? Will they go in the first level? Will they go in the S? Can I do that? Can I put them there, like a parking deck? Now you got a 3rd car. What are you going to do with the 3rd electron? Can I put it in the first level? No. There's no other place for it. But where do I go then? You got to go up to what? energy level number 2. And here's the beauty. What is the first element in period number 2? Who's the first element that would need a second energy level? Lithium. So he goes up there and he goes to the second level. Hey, I'm in the second level. Where are you going to put my car? We got a nice little place there called an s orbital. Wait, I thought you had a 1s. Yeah, but this is a 2s orbital. Yeah. Here's a 1s orbital, but in the second energy level, we got a bigger s orbital called 2s. Oh, okay, I'll go there. Park my car there. So count up the total number of electrons here. Ready? 2 plus 1, 3 electrons. Configuration, tell me the configuration of lithium's 3 electrons. 2 of them are in the 1s orbital, and 1 of them is in the 2s orbital. Get that? Is that 3 electrons? Okay, yes, go ahead.
Why would you leave the 1s2 there?
Because, okay, this thing called an orbital, you can only put at the very most 2 electrons in an orbital. So if you have 3 electrons, how many of those 3 can I put here? 2. So I fill it up, 1s2. But now you got an extra one. Where's it going to go? It can't go in the first level. All right, jump to the second level. And who's waiting for it in the second level? Another s orbital. Do the next one. Ready? Now you have 4 electrons. Let's do beryllium. Let's do beryllium. He has 4 electrons. Let's go around the room. You should be catching on a little bit to this. Daniel, help me out on this one. Where are you going to park 4 cars in the electron configuration parking deck?
It'd be like 1s2.
That's where you put the first 2 cars.
2s.
Uh-oh. Can you put 2 in there? Can you put 2 in an orbital? Yes. But no more. You can't put any more in a 2s, right? An orbitals can only hold what?
2.
That's it. All right, now a little excitement here. Kind of, a little bit of excitement. Look what happens here. Whoa, way over here. Something new is happening. Something new is happening. Boron has 5 electrons. Where in the heck are you going to put 5 electrons? All right, let's do, Kyle, help me out. What are you going to do? What are you going to do the first 2 of the 5? I'm going to put 2 of them there. Yeah, you can't put more than 2 in an S. But now, now you got one. I understand. I would have done that. I would have said 3S. But guess what? The second energy level, or the second level of the parking deck, is bigger. And I have room for an S orbital, but I also have room for how many P orbitals? Look at the shape. Dumbbell shape. Now you might say, well, why is it that shape? I don't know. I'll ask God one day. But I do know that S orbitals have this shape and P orbitals have a weird shape. Now, when I was your age, I used to think this. Actually, I don't know if my teacher did that when I was your age. I might have said, well, then I bet the electrons are going like figure eights. We have no idea what they're doing. But 90% of the time, they're in here or here or here. So guess what? In the second parking lot, the second level of the parking lot, I got a nice little space here called an S, and I can put 2 cars there, and then I got a P space, and another P space, and another P space. So here we go. Let's do it. Finish out for me, okay? Kyle, finish it out. You've never done this before in your life. I'll give you a clue. You're still in the second energy level, but you ran out of, you can't put any more here, so you got to put one where? What kind of orbital are you going to use now? A P orbital. And how many are you going to put in there? Yes. Look, it's working. So how many total electrons is that? 5. I did. I parked them. I parked all 5 of my cars. All right, Isabella, louder than you think you can. How about that? As loud as you can. Let's do the next element. And the next element is carbon. All right, where are you going to park your 6 electrons?
Okay, so 1s2.
Yes.
2s2.
Yes.
And then 2e2.
Yes. You did it. Does that make sense to you? All right, so you put 2 here, then you put 2 here, and then you put 2 somewhere in here, didn't you? All right. Your turn. You ready? Zach? What's the next element? What? What? N. What's the N? Nitrogen, right? Isn't that nitrogen? Yeah. All right, where are you going to park 7 cars? Yes. Yes. Now, even though each orbital can only hold 2, I have 3 p orbitals. So I can put more than 2 total, can't I? I can put 1 here, and then 1 here, and then 1 here, and then another one, and another one, another one, can't I? I could put 6, couldn't I? 6. How many are you going to put there?
3.
How many? That'd be too many. How many electrons are you going to park? How many cars you have to park? 2, 4. You already parked 4. 3. Okay, there you go. You okay on that? Everybody got that? This is working. Now, it is true that if you wanted me to split this up, I like what you're thinking. I could have said in the first P you put 1, in the second P you put 1, and in the third P you put 1. I could have done that, but I just combined all the P electrons there. And I put P3. Get that? Because when I say P, it means all of these right there. Yes?
So how high can you go out from the
Okay, for the P orbitals? Okay, watch. I can put 2, 4, 6. I can put 6 in them. So I'll never put a number higher than 6 in the p orbitals. I'll never put a number higher than 2 in the s orbitals. All right, whose turn? Julia. What's the next element? Oh, we're doing well. Come on, keep going. What is it?
Oxygen.
Okay, so that's 8, right? Where are you going to park 8 cars?
So 1s2, 2s2, 2p4.
Yes? 4? Okay. All right, go ahead. Delaney. Next element. F? Fluorine? Where are you going to park 9 cars? 2p what? Yeah, count them up. 5 plus 2, that's 9. Okay. All right, May.
Neon, you have 11.
No, I think 10.
10. 1s2.
Yes.
2s2.
Yes.
2p6.
Oh, yes. Yes. All right, you get the hard ones. All right, you get the hard ones. Number 11, go.
1s2. 2s2. 2p6.
Uh-oh. Look. No more parking spaces. In the second energy level, no more parking spaces. Where are you going to put it? It could be, but guess what? In every level, guess what's waiting first? Yes. Say it again. Yes. Look. 11. And you know what? Here's the beauty. Here it is again. What's the first element to need a third energy level? Look. What's the first element in the third period? It's sodium. It's the first one to need a third energy level. And we're not going to do that Saved by the Bell. That was a TV show. So here we go. Sierra, give me one more. We got one more element. Are you doing magnesium? All right, where are you going to park 12 cars?
It would be 1s2, 2s2, 2p6, 3s2.
Wait, can you put 2 in an S? Yes. Can you put 3 in an S? Oh, that's correct. That is correct. So now, all right. Is that enough for today?